Hello, everyone. Welcome to another series of talks today. This is the Division of Chemical Physics, Frontiers in Chemical Physics, where as a division, we're serving the DCP community, but also the chemical physics community more broadly with the series of cutting-edge chemical physics research talks. And so I hope you've been enjoying the last several we've had and are looking forward to continual exciting talks. So today I have the pleasure of introducing our today's speakers, Professor Bryan Changala and Professor Spiridoula Matsika. So first, Professor Bryan Changala is from Boulder. He got his bachelor's degree in chemistry and physics from MIT. Received his PhD in physics in 2019 from the Yi Group at Gila. And from 2020 to 2024, Bryan was a postdoc researcher with Mike McCarthy at the CFA Harvard Smithsonian Institute. And since 2025, he's been an associate Gila Fellow and assistant professor of physics. And their laboratory is interested in open questions in astrochemistry, fundamental physical chemistry, and quantum molecular science. Bryan, go ahead, take the floor.
Thanks for the introduction, Nathan, and I want to thank both Nathan and Zeke for their effort organizing this series. It's been great, and I'm really pleased to be here today. Just let me get my slides up. All right, there we go. Well, fantastic. So today I wanted to kind of use this as a chance to introduce you to me and to some of the work we're starting here in my kind of very new laboratory at Gila. We got started about 10 months ago here as an independent group. And my lab focuses on using a variety of precision optical and microwave spectroscopies to study high precision and quantum state resolved spectra of a wide variety of exotic molecular systems that tend to be highly reactive, refractory, or short-lived. And we use the detailed information from the spectroscopy to generate molecular scale insights relevant to problems in astronomy, to fundamental molecular physics, and trying to use gas phase systems as a way to understanding condensed and extended matter. So today I'm only going to tell you kind of about a portion of our work centered on advanced infrared light sources, in particular frequency combs, and how we're using this laboratory tool to advance two very different types of molecular science. One, UV-driven ion chemistry in the interstellar medium, and the other is kind of more fundamental molecular physics, trying to push the frontiers of the types of precision molecular spectroscopy that we can do and increase the system size and complexity to systems as large as these kind of prototypical fullerenes, so C70 and C60, for example. So we're going to start with this interstellar astrochemistry direction. If you allow me to be kind of very grandiose, I'll make this statement that we're all made of carbon. Carbon's the most chemically important element for life. And one thing that astrochemists are very interested in is understanding what is the origin and fate of carbon, and in particular, what was the state of carbon when it was delivered to new solar systems like our own and kind of seeded the organic material that ultimately led to life on Earth and potentially other habitable planets. And so the way astronomers try to answer these questions is, of course, they cannot go back in time and look at our own solar system. But if you have powerful enough telescopes, you can search our galaxy for other objects that are at an earlier stage in their galactic evolution or their stellar evolution, and try to learn something about their chemistry and build a comprehensive model of carbon chemistry over the life cycle of a typical star and planetary system. So one particular object that is highly studied for this sort of astrochemical insights are nebula or stellar nurseries. And of course, one of the most famous nebulas to all of us back here on Earth is the Orion Nebula. That'll be quite familiar to you. So here's the Orion Nebula at the bottom of Orion. If you zoom into that nebula, here's kind of a bird's eye view of the entire nebula. If you zoom in, again, another kind of factor of 10 to 100 in the middle of this, you see an object that's known as the Orion bar, which is this kind of molecular cloud here that is being irradiated by intense far ultraviolet radiation from a nearby massive star. And this UV irradiation kickstarts a complex chain of ion molecule chemistry that astrochemists believe is responsible for some of the first stages of organic chemistry in these types of objects. And indeed, recently, some of the first observations performed by the mid-infrared instruments on board the James Webb Space Telescope can take extraordinarily detailed pictures of objects in these nebula. So again, if you zoom in another factor of 100 or so, you can see this blob here in the lower right. This is a protoplanetary disk called D203506. And this protoplanetary disk, you can think of this as being a kind of a baby solar system. It's an early stage of its evolution where there's a star has begun to form, but there are not planets as they are in kind of our own mature solar system. And you can hope that by understanding the chemistry in a source like this, you can learn something about the chemistry that that directed the fate of carbon in other typical protoplanetary disks. And so the kind of the simple model for how this chemistry works begins with free carbon atoms in these clouds, which are efficiently ionized by this intense ultraviolet radiation. This generates carbon cations. And this carbon cations react rapidly with the most common collision partner in these clouds, which is, of course, hydrogen, which is, by far dominates the densities of any other molecular species in these clouds. And after a few rounds of collisions with hydrogen, you can end up at a relatively stable carbocation, CH3+. And this can go on as a kind of springboard for more complex organic molecule formation using a sequence of kind of reactions with H2 and recombination events, and then reactions with additional carbon ions to form more and more complex hydrocarbons. And you can also use these types of mechanisms to incorporate heteroatoms like oxygen and nitrogen. And these types of ion molecule chemistry is believed to be very efficient at the conditions of these UV irradiated clouds and may give rise to a very complex organic chemical inventory that seeds the later stages of chemistry in these sources. And so if we want to understand these complex ion molecule chemistry reactions, the way to do that is by quantifying the important reactive molecules by spectroscopy. And in particular, for these sorts of systems, IR emission is the mode of spectroscopy that is particularly important. And that's because these UV irradiated clouds tend to be quite warm, on the order of hundreds to maybe 1,000 Kelvin. And this means their fundamental vibrational excitations are readily populated. And these excited vibrations emit infrared light that can be detected with sensitive telescopes. And indeed, one thing I really want to emphasize is that essentially everything we know about the chemistry outside our own solar system comes through us through spectroscopic observations. And so there's a wide range of energy scales and physics and kind of astrophysical scales is funneled through, that information is funneled through molecular spectroscopy. And so having a very detailed understanding of the not just energy levels of these molecules, but also their emission properties, so their things related to spectroscopic intensities, is critical for being able to generate astrophysical and astrochemical insights through spectroscopy. And so just an example of kind of the very rich infrared rotationally resolved spectra that you can observe in these types of sources. This is a very recent example of the emission spectra of CH3+ from the Orion bar, measured with the James Webb Space Telescope. And in fact, this was the first discovery of interstellar CH3+ by this fantastic paper by Olivier Bernet and his coworkers that was published in Nature a couple years ago, and that we subsequently did some follow-up theoretical and laboratory spectroscopy work to help validate those assignments and findings. And as you can see, there's incredibly detailed, rich information here. The only way to learn quantitatively, how much of these molecules there are, what are their astrophysical conditions, and what is their potential chemical history, is by having a very detailed understanding of their spectroscopy. But the problem for these types of molecules is that at the wavelengths that are most relevant to James Webb and other space telescopes observations of these warm clouds, namely long wavelength infrared, kind of out to, let's say, 5 to 25 microns or so, there's very little reliable laboratory data of these small molecular ions at these wavelengths. And that actually may come as a surprise given that infrared ion spectroscopy has been alive and well for decades now. And again, one of the primary reasons this data doesn't exist is that one, ions are hard to make in the lab. You need very sensitive techniques. And second, the wavelengths that we need to access to do this type of spectroscopy are also difficult to generate in the lab with the kind of spectroscopic properties that are favorable for doing the sorts of precise high-resolution spectroscopy that we need. And so what I want to talk to you about today is primarily the sorts of new infrared tools that we are developing in our laboratory here at GILA in order to enable this type of ion spectroscopy. That's primarily what I'll focus on. This type of work involves a lot of traditional physical chemistry laboratory techniques as well to make these sorts of reactive systems. I won't talk too much about that. And our group also does a lot of ab initio quantum chemistry and to both predict and interpret these spectra at very high accuracy. So we do very kind of high level electronic structure and nuclear motion calculations to aid these experiments. Again, I won't talk too much about that either. So let's focus on this IR laser spectroscopy aspect of these. So the big problem is that traditional infrared light sources don't meet the laboratory we need for doing this type of spectroscopy. We need light at long wavelength, in the long wavelength region, so let's say out to 20 microns or so. We need very high spectral brilliance in order to have enough sensitivity for the detection. Again, the sorts of measurements we do are based off of just linear absorption. And so that makes you need a relatively intense light source in order to beat the noise limits of kind of noisy detectors. And lastly, we need very high resolution and spatial and temporal coherence in order to get very high wavelength resolution needed to compare with these astronomical observations. So you could pick your favorite infrared light source. It may be something as simple as like a glow bar that's in a benchtop for a transform interferometer. This has great spectral coverage, but very low brilliance and very low resolution. Something like a synchrotron can increase your brilliance, and if with a sufficiently large spectrometer, you can get very high resolution. But of course, the synchrotron is a little bit larger than my startup budget, so that's not the sort of thing we can do for a laboratory environment. There's been great advances in semiconductor infrared lasers, so particular quantum cascade lasers. These are great CW light sources, but it's much difficult to turn these into a widely tunable light source that covers the entirety of the mid and long wavelength infrared region. And so this light source that we turn to in our lab is optical frequency combs, which kind of can meet all of these needs in a very elegant and powerful way. So frequency combs have been used for molecular spectroscopy now almost since their invention about 25 years ago. That said, they're still a relatively new tool to the physical chemistry and chemical physics community. So I just want to kind of briefly remind you what a frequency comb is and why this is so useful for our types of spectroscopy. So in brief, a frequency comb is an ultra-fast pulse laser that just spits out a repeated pulse of trains, a repeated train of pulses that are separated by some repetition period, which I'm calling tau rep here, and have a particular phase of their electric field underneath these ultra-fast envelopes. And what makes a generic ultra-fast laser into a frequency comb is simply controlling the timing and phase of these electric field pulses at a very, very high degree of precision. In our experiments, that's about 1 part in 10 to the 10 level of precision. And if you can control the pulses at this level of precision, then the optical power spectrum of this pulse train is not just a broad continuous spectrum that you would expect for a single ultra-fast pulse, but because each pulse has very strict phase coherence with its next pulse, and in fact, many, many pulses later, that optical spectrum actually turns into a sequence of uniformly spaced, narrow optical modes that are each like a very narrow CW laser, where they're spaced by the repetition rate of this comb, which tends to be on the order of about 100 megahertz, or roughly a hundredth of a wave number, or that sort of thing. So this gives us a frequency ruler that has a very fine spacing that allows us to do very high resolution spectroscopy. That's why we really like to use frequency combs. So what's new in frequency comb technology that we didn't have, say, 5 or 10 years ago? And that's having efficient ways of generating long wavelength infrared frequency combs. And traditional combs are generated with near infrared fiber lasers or visible ultrafast lasers like TISAF lasers, for example. Starting with these relatively short wavelengths, it is difficult to convert these to the very long wavelengths we need with good power efficiency. And so one of the great advances in ultrafast laser technology that's kind of become available now in the last, say, 5 or so years is new gain media for that initial ultrafast laser, in our case, a chromium zinc sulfide laser, that allows us to directly generate our initial comb at 2.4 microns, so well into the mid-infrared wavelength at very high power, several watts. And what's key is that driving nonlinear conversion processes, in particular difference frequency generation, with this very long 2.4 micron wavelength light is much more efficient than driving it with shorter wavelengths like 1 or 1.5 micron. And this means you can generate long wavelength lights using difference frequency generation at really high power efficiency. So for example, by just sending a single pass, sending one of these 2.4 micron combs into a piece of a ZGP crystal, you can generate with a single pass hundreds of milliwatts of long wavelength infrared power with very high spectral bandwidth. You can cover in a single shot about an octave or so of spectral bandwidth. And this is really what's the game changer for the sorts of spectroscopy we'd like to do. So an example, so we just got one of these systems up and running in our lab, and we're successfully generating long wavelength infrared light with one of these. Here's some real data from our lab showing a single shot spectrum of this difference frequency generation output pumped by this mid-infrared comb. This shows you about an octave span from 6 to 12 microns, and it's hundreds of milliwatts. That's a lot of power for any sort of spectroscopy that we want to do. In order to actually measure the spectrum of our comb, we need some way of measuring the intensity of each individual comb mode. And the simplest way to do that is just to build a high resolution interferometer that allows you to interferometrically separate the power of each comb mode, just like a benchtop interferometer does. In our case, we need sufficient resolution to resolve each of these comb modes, which are very closely spaced. And this means you need a very long interferometer. So we've just finished building a homemade 8-meter interferometer, so it's relatively long. That gives us enough resolution to individually resolve these comb modes. So this kind of inset I'm showing you is real lab data showing the resolved comb mode structure. Each of these comb modes is like an individual laser separated by 80 megahertz or so in the optical. And our interferometer is just long enough to resolve these actually by a factor of 2. So we can kind of see the power go almost all the way down to 0. Also, one thing I'll emphasize is that the line width you see here is just an artifact of the interferometer, which in this case is about 40 megahertz. The true optical line width of these combs is actually many orders of magnitude narrower than this. It's just not resolvable by the interferometer. And that means your effective spectroscopic resolution is not limited by the interferometer. It really is the line width of the comb, which is about 1,000 times narrower than the interferometer line width. So again, that's another great benefit of comb spectroscopy. If you want to compare this to those other kind of traditional long wavelength light sources I mentioned before, I'll point you out to comparisons with the cyclotron, say. So the spectral brilliance of this type of tabletop broadband high-resolution light source is a few orders of magnitude higher than the traditional cyclotron light sources that people use for this sorts of infrared spectroscopy, like the SLS or the ALS, for example. So you can, at least over this long wavelength infrared range, really think of these sorts of light sources as tabletop cyclotrons. And I think that's a real powerful way to think about it. All right, so if we have this great frequency comb on our table, how do we use this to measure spectra? So the simplest way is just to stick this light source through a sample of your molecules, use this really high resolution interferometer to read out the power of each comb mode, and then just measure that with and without a sample and measure an absorption spectrum. And indeed, that's the usual way we do this experiment. That's called direct absorption comb spectroscopy. And by doing this, you can benefit from both the high resolution of the comb and the very broad spectral coverage. Typically, however, our absorption signals are very, very weak. They might only be, say, part per million sorts of absorption levels, and that's very difficult to measure. So in order to improve that absorption, we usually couple our combs into high finesse optical cavities that allow us to increase the effective path length by about 4 orders of magnitude, giving us path lengths on the order of 10 kilometers or so. I won't go into the details of how we do this in a stable fashion. I'll just say that what's really elegant about this idea is that the cavity resonance structure of this Fabry-Perot cavity, of course, exactly matches the equally spaced structure of the comb teeth. So it's possible to efficiently couple every comb tooth, if you want, into its own cavity resonance and have a very highly kind of parallelized and efficient cavity-enhanced absorption spectroscopy. All right, so we're now in our lab building up to use this comb to do this to measure these sorts of ions that I mentioned before. And so We have a long history of ion chemistry techniques from the physical chemistry community that tells us how to make these ions, and so we don't need to reinvent the wheel. We're using positive column glow discharge cells based off of work that was pioneered by people like Takeshi Oka. You can think of these cells as basically neon signs that you dope a few molecules into, and this makes ions pretty efficiently, though that's still at relatively low absolute concentrations. Again, the way this experiment works is that we couple the light into the cavity, and then we read out our spectrum on an interferometer. And if you look at a typical interferometer kind of spectrum of this, which I'm showing you with this little black spectrum on the side here, our comb spectrum occupies a relatively narrow part of the total kind of spectroscopic bandwidth we have, which is ultimately sent by the response of our detectors. But we have a relatively narrow comb. Even though this is a very broadband infrared comb, it's still a relatively small fraction of our kind of readout bandwidth. And so an important aspect that's going to make these experiments sensitive enough and selective enough to measure these kind of fleeting and elusive ions that we're interested in is to remember this motto that I'm trying not to forget, is to never let bandwidth go to waste. And so what do I mean by that? So the first thing to realize is that these types of discharge cells are actually very noisy environments. Right? There's an AC plasma that's going back and forth at audio frequencies. There's a lot of dispersion in this cavity, and that actually makes coupling your comb light to these very narrow optical resonances difficult. And the mismatch between these resonances can lead to a lot of intensity noise that limits your sensitivity. So what's very important for us is to use a different type of comb coupling technique where we continuously sweep our light in and out of resonance, just like a cavity ring down spectrum, but are still able to measure these ring downs using an interferometric technique. And so basically you can think of the ring down as being an amplitude modulation of your comb light that leads to modulation sidebands in your interferometer spectrum. And if you're very careful about how you demodulate the spectrum, you can recover the full ring down time curve using interferometric readout for each comb mode individually. And so this idea was demonstrated just very recently by my colleague down the hall, a student named Qizhong Liang, who's in Junyi's group. And it's a really elegant technique for doing comb mode resolved interferometry, which is kind of the perfect method for this sort of ion plasma spectroscopy. We can go one step further by taking advantage of that. We're trying to look for charged species, which are really at about a part per million relative to our neutral carrier gas. And that makes them, of course, hard to distinguish from this background of neutrals. But because we have an AC discharge, these ions are being velocity modulated at the discharge frequency. And so this actually leads to another sequence of sidebands on the spectrum that you can use to selectively measure the signals from just ions. And of course, this is a classic laser spectroscopy technique by people like Oka, Rich Sakeley, Ben McCall, and others that we are looking forward to kind of implementing with this cavity ring down comb spectroscopy that allows us to make the most use of the bandwidth of our experiment to kind of encode the most information and sensitivity in our spectra. So we're actively building this experiment right now. I just wanted to kind of finish this section by showing you how quickly these sorts of laboratory results that we will be acquiring kind of make their way to the astronomical community. So this early CH3+ analysis that I told you that was only about a couple of years ago has already led to new detections of CH3+ in a diverse set of astronomical objects, including oxygen-rich planetary nebulas and other protoplanetary disks. And in fact, as you can see from these spectra, CH3+ is not a like minor species in these, right? It really it dominates the infrared emission at certain wavelengths, and we expect that similar data that we're going to be able to measure in our lab on other small carbocations will similarly make its way and enable new astronomical discoveries in a very accelerated rate. All right, so the last minute or two here, I just wanted to close up with kind of a flavor of a different direction that we can go with these sorts of advanced infrared light tools for doing fundamental molecular physics. Some work that I did during my PhD here at Gila about almost 10 years ago now already was trying to apply these infrared combs to studying quantum state resolved spectroscopy of larger and larger molecules and investigate what's the limit of molecular size we can do this type of precision spectroscopy. And in there, the big challenge is actually cooling the molecules down to their vibrational ground state so that the spectrum isn't completely congested with hot bands. And so for large molecules, this is difficult because they have a huge heat capacity. But by using techniques like cryogenic buffer gas cooling, you can do this efficiently. And we showed that molecules like C60 can be indeed cooled to their quantum mechanical, their vibrational 0 point level. And if you can cool them to that level, you can indeed measure total state resolve, internal state resolve spectroscopy of these sorts of molecules at infrared wavelengths. So this is an example of a rotationally resolved vibrational band of C60. If you zoom in here, indeed you see individual, very well-resolved lines that correspond to the quantized rotational motion of this large molecule. And these have very narrow line widths, and these say things, processes like IVR and things like this are indeed very, very slow in these large molecules, surprisingly so. And really what I want to emphasize is that we now have the tools for detecting a molecule where every degree of freedom, every electron, every vibration, its rotations, and in principle nuclear spins are in a very well-defined quantum state. And this allows you to start asking different types of questions of large molecules. And so as an example of that, just some recent results that came out of this experiment over the last 10 years or so include fundamental tests of kind of quantum indistinguishability, right? C60 is a collection of carbon-12 bosons, and that leads to very striking bosonic spin statistics, which have now been experimentally confirmed. You can do kind of traditional PChem things like measuring state-resolved collisional cross-sections with C60 now that you have state-resolved access. And you can study kind of more generic quantum dynamical aspects like ergodicity, when you, in particular for the rotational degrees of freedom, in things like C60, again, now that you have access to quantum state resolve. So I won't discuss any of these experiments in detail. I just want to give you a flavor of one project we're now planning on doing with this infrared comb spectroscopy of fullerenes. And that's this idea that molecules are really nature's own atomic lattice. So kind of as a thought experiment that we hope to soon to be a real experiment is to consider the carbon-13 C60 lattice that's I'm showing here. So this is a collection of the hyperfine structure of this molecule is a collection of 60 identical spin 1/2 systems. And so it has a huge Hilbert space, about 2 to the 60. That has an energy scale that's very low, about kilohertz energy scale. But we can prepare this molecule in the gas phase, in its vibrational ground state, and essentially prepare a lattice of these spins at absolute zero in the rest frame of the molecule. And so the sorts of spectroscopy that I just showed you with our infrared combs are probing this, low vibrational degrees of freedom. What we're suggesting here is if we can improve the resolution of this experiment a little bit more, we should be able to probe this hyperfine structure that is at about the kilohertz scale. And if you can probe this, you're essentially measuring kind of the density of states of this very large Hilbert space. And that means you can start asking questions that you would normally ask of a mini-body system. Things like, is there a phase diagram that describes the statistics of this Hilbert space? And what are the tunable parameters of this phase diagram? Things like external fields or kind of quasi-external fields. Things like, is the molecule rotationally excited? Is it vibrationally excited? That change the effective Hamiltonian that these the nuclear spins, that their dynamics evolve on. In other words, you can kind of think of these sorts of large molecules as really be molecular analogs of the sorts of atomic optical lattices that my AMO physics colleagues here at GILA study with great precision and really advanced tools. In this case, we're trying to use molecules and the global stationary Hilbert space structure that we can probe with frequency domain spectroscopy to learn something about the dynamics or emergent kind of phase diagram type properties of large but closed quantum systems. So this is the direction that we're pushing toward here in the C60 project, and we're really excited to kind of see if there are these new sorts of fundamental questions that we can ask of molecular systems. All right, so I'll finish there. Just remind you that really all these advances in astrochemistry, molecular physics are based off of the technological advances in infrared light sources that we're able to achieve, and infrared frequency combs are for us kind of the most important player in that. I'd like to just finish thanking the first members of my group here at GILA, in particular Matthew Smith and Kenny Wilson, who are working on our infrared frequency comb project, and the members of the fullerene collaboration here at GILA that's led by PIs Jun Yi and David Nesbitt. And I really like to point out Yatu Chan, who's a graduate student working on this project right now and who's doing a fantastic job taking it to the next level, and our kind of former members of this team who I know many of you know well, Marissa Weichman, Lilio, and Dinah Rosenberg. Thank you.
Fantastic. Thank you, Brian. For now, we're heading to the Q&A session. So if you would like to ask a question, you can maybe do so by either typing it into the Q&A feature down below to set the Q&A question mark bubble to type in your question, or otherwise you can raise your hand and I can unmute you to ask your question. Maybe to get us started here, we have a question from Matthew Eager. Their question is, do we know that C plus carbon cation +1 is the highest oxidation state?
Oh, that's a good question. I actually don't know the status of what the observations are, but my initial reaction is that there's not going to be much more. If there's higher C2 plus, C3 plus, they'll be at a much lower concentration. You can indeed observe highly charged ions, atomic spectroscopy of highly charged ions in these irradiated environments. But recall that typically photon energies higher than the IP of hydrogen atom, those photon energies are highly depleted because they get absorbed by ionizing hydrogen. So that's 13 eV or so. And so it's going to be difficult to ionize these atoms to 2 plus or higher because the radiation density is much lower at the relevant photon energies.
Very good. Okay, very good. All right. I'm seeing no other questions in the chat, nor anybody's hand raised. Carl Arukua. Okay, you may ask your question.
Hi, thanks for the nice talk. I have just you said it's a thought experiment for the homoisotopic C60. So I guess it's going to be really hard to make that without any contamination with carbon 12s in any of the molecules. And I was curious about the issues that come out of that. So for example, if there's enough, even with your tremendous resolution, whether that is enough to distinguish, a contamination by say 1 or 2 carbon 12s in the molecule. And if it is, I wonder if is there anything interesting about the different isotopomers, for example, with 2 carbon 12s, but in various different locations. Would there be anything interesting to learn if you could see that? Thanks.
Yes. Thanks for your question, Carl. So the short answer, yes, there's a lot of interesting stuff to learn from isotopic substitution and different isotopomers. So on the carbon-13 sample side, in fact, our team does have a purified carbon-13 C60 sample in production right now with a third-party synthesis, third-party chemical vendor. We need a isotopic purity kind of comparable to that of carbon-12, i.e., we need more or less 99% carbon-13C, and that's because at 1% of the other isotope then only about half of your sample will be pure carbon-13 C60. About a third of it will have single substitution, and the rest will be higher substitutions. And of course, that's just from the combinatorics and the statistics of that substitution. So that's what we need is roughly 99% purity, and that's we actually have a sample that should be on its way soon that we can start really looking at the spectra of carbon-13 C60 with that. Already with the normal distribution where it's mostly pure carbon-12 C60, we have various in the experimental laboratory data. We do have evidence of singly substituted carbon-13 C60 in there. It should be relatively high fraction relative to the pure isotopolog. Of course, for the singly substituted, every substitution type is the same. So there's only one singly substituted molecule, and that hopefully makes it analyzing its spectra a little bit simpler. With the other isotopomers, we're not particularly hopeful that with higher order isotopers, we're not particularly hopeful that we'll be able to do much with our types of spectroscopy, because as soon as you have 2, let's say, there's already so many distinct isotopomers that their spectra are going to be kind of convolved and mushed over each other. Even with the singly substituted carbon-13, even though there's just one isotopomer, it already breaks the symmetry of the molecule enough that this is an open question, whether much of the well-resolved low vibrational fine structure we observe, how much of that survives. To 0th order, we know what it should look like, but it's unclear if even this very minor break in symmetry turns on intramolecular anharmonic processes, like IVR sorts of things, enough to begin to wash out that spectroscopic structure. So that's an open question. That's an even low resolution data on the singly substituted isotopologues would be very useful, particularly for actually returning back to astrochemistry. That singly substituted data would be particularly useful for looking at the infrared emission of fullerenes, which have been observed in space. If you can quantify the carbon-13 fraction of carbon in fullerenes using the different infrared signatures of these different substitution numbers, this gives you actually a very powerful probe for measuring isotope ratios in fullerene-rich environments. In fact, fullerenes are kind of the perfect way to measure isotope ratios because you get this factor of 60 amplification in your isotope sensitivity because every carbon atom is identical. And that's, most carbon-containing molecules do not have 60 identical carbon atoms. So that's a special feature of fullerenes.
Fantastic, Bryan. Well, thank you so much for your talk here. So in the interest of time, we'll continue on with our next speaker, Professor Spiridoula Matsika. And so as they're sharing their slides here, just a bit of information about Spiridoula as Professor of Chemistry at Temple University, and received her bachelor's degree at the National Kapodistrian University of Athens in '94, PhD in chemical physics from Ohio State University in 2000, and spent some years as a postdoc at Johns Hopkins University, and she's been at Temple since 2003. Her group is interested in theoretical descriptions of electronically excited states, non-adiabatic dynamics, and conical intersections in molecular systems. Spiridoula, the floor is yours. Go ahead, please unmute yourself.
Okay, can you hear me?
Yes.
All right, okay, thank you for inviting me to be part of this series. It's really great to be here. So I will go ahead starting talking about non-adiabatic dynamics. Before I move on to my work, I want to start by advertising the special issues. So David Yerkoni was a pioneer in non-adiabatic events, so I think it's very appropriate here to advertise the special issue. David passed away, unfortunately, about a year ago, and we celebrate his memory by the special issue, so everybody is welcome to submit. Okay, so what we do in my group is we try to understand better reactions that they are initiated by photons or electrons. And that means that we are interested in reactions that happen on excited states. So the basic idea is that we have excited states that are more than that interact with the ground state and other states. So in order to understand these kinds of problems, we really need to understand the coupling between different potential energy surfaces. So that brings us to this non-adiabatic dynamics. So we really need non-adiabatic dynamics to do that. So what do we mean by that? So in general, when we apply theoretical tools to understand molecules and reactions, we do that in two parts based on the Born-Oppenheimer approximation. So we start by solving for the electronic motion. So we solve the electronic structure part first. And that gives us the potential energy surfaces that the molecules can travel on. And then as a second step, we can solve for the nuclear motion. So in the Born-Oppenheimer approximation, the nuclear motion is the nuclei evolving on a single potential energy surface. But if we have more than one surface, then the Schrödinger equation has these additional terms. And these additional terms involve the coupling between the surfaces. So this is obtained directly from the Schrödinger equation. So we have these couplings that they are very important in non-adiabatic dynamics. So when we study these problems, we have to evaluate these couplings and see when this transition between different electronic states is important. Furthermore, these couplings are inversely proportional to the gap between the different electronic states, which gives rise to the importance of conical intersections. So the conical intersections are the points where the two surfaces will become degenerate And there we have the most efficient coupling. So we have an infinite coupling between the surfaces. So these are also become very important in how we understand these problems. All right, so this is the fundamentals of how we think, what we mean by non-adiabatic dynamics in molecular systems. And now I will say a little bit of actually of how we do that in my group. So again, as I was saying earlier, the first step is always to solve for the electronic structure. And we do that using multi-reference methods. So because we need to describe equally many electronic states, the multi-reference methods do that because they have many configurations treated at equal level. And there are many variations of multi-reference methods, and we are using a lot of them. And I will not go into details about which ones, yeah. So then the second step is, as I say, the nuclear motion on these potential energy surfaces. So we don't do that using the Schrödinger equation. It would be very expensive to do quantum dynamics. But the good thing is that the nuclei are much heavier than the electrons. So we can assume that they are behaving classically. So we study the motion of the nuclei on the surfaces using classical mechanics, using Newton's law, basically. And the only thing that is different here is that actually we have many of these surfaces. So we have to have mechanisms for the molecules to hop between the surfaces. And we use the trajectory surface hopping approach, which is a very common approach in this field, where using the non-adiabatic coupling, we can estimate probabilities for the coupling between the surfaces. And that's what we use. Yeah, and also to because we are trying to approximate a wave packet, we have to start from a swarm of trajectories. So we don't do one trajectory, but we have to do hundreds of trajectories to imitate what a wave packet will be doing. Okay, so the next step, so this is how we would do the dynamics to see what the molecules are doing on excited states. But in order to really understand what molecules are doing, I think it's very important that actually we work together with experimentalists. What experimentalists do to understand excited state dynamics is some type of pump probe spectroscopy. So this cartoon here shows the basic idea. So the molecules are excited with some laser. And then after some time, a second pulse, the probe pulse, is coming in and can do different things for the molecule. So that creates the signal. And then if we watch the signal as a function of this delay between the pump and the probe, we can find information about the lifetime of the excited states and so on. So there are many variations of pump probe experiments. And we have collaborated with experimentalists in some versions of those. So here I show some of the things that, some of the spectroscopies that we have worked on. So time resolved photoelectron spectroscopy, ultrafast electron diffraction, Coulomb explosion, and Thomas Weinak and Martin Centurium are the people that we have, at least the things I will show in my talk come from their experiments. And also, so there are two ways that you can compare with experiment. One is that you can just do the dynamics and then you can look at timescales and just compare the lifetimes. And I will argue, especially in this talk, that this is not enough. So we need more than timescales to actually know what the molecules are doing. To do that, it's also important that we calculate the signal. So not only the dynamics on these surfaces, but also calculate the signal, whatever the signal may be, and compare directly with the experiment. And in that case, we are comparing apples to apples. So what I want to talk about today, just to highlight some of the important things about excited state dynamics and non-adiabatic dynamics, we'll use two examples. One is cis cyclooctadiene. And this example, I will highlight how we can compare different kinds of probes. So there are more than one experiments, and using theory plus the different kinds of experiments, we can actually learn more about the molecule. So this multimodal approach, which is very important in the field these days, can give us more detailed information about what the molecules are doing. And in the second example, I will talk about nitrophenol. And here the highlight will be how you can have very different dynamics if you use different excitation wavelengths. And that should be taken into account. All right, so just to start with the first system. So the first system, again, is cyclooctadiene, which is shown here. So this molecule has 2 double bonds. So it's an extension of, one can think of butadiene, which is a system that has 2 double bonds. And think about what the photochemistry will be for this molecule because of that. So for molecules with double bonds, the photochemistry is initiated by the motion along the double bonds. So thinking about ethylene, which is the simplest organic molecule that has double bonds, when the molecule is excited, twisting around the double bonds creates these conical intersections with the ground state because you have the double bond, and when you twist it, you decouple the 2p orbitals. So you can think now that you have 2p orbitals that they are degenerate. But also that is not enough. You also need to pyramidalize one of the carbons. So that's what creates the conical intersections, and that can create a very fast way to go to the ground state. So when you have 2 double bonds, you can do that along each one of the double bonds. And these are, so now this is a potential energy surface cartoon. So it's just a linear interpolation that shows for this molecule that after initial excitation, the potential energy surface is more or less barrierless to reach this conical intersection here. And the conical intersection involves twisting around the double bond and pyramidalization. And you can have pyramidalization on the inner carbon or the outer carbon, and that creates different types of conical intersections. But also you can have twisting or both of the double bonds at the same time, and that creates a different type of conical intersections. So there are different types of conical intersection in this molecule that can facilitate the radiationless decay to the ground state. So the lifetime of the excited state is very short. So when we did the dynamics and we compared, so initially we compared with time-resolved photoelectron spectroscopy. So I will not go into details how we do these calculations, but this is just the final result that comes from, so the theory here involves doing the surface hopping, trajectory surface hopping on the excited states, and then calculating the time-resolved photoelectron spectrum to do what the experiment has done. And that is this decay signal here. The experimental curve is the red curve. So both theory and experiment predict that after this molecule is excited, it will decay very fast to the ground state. The experimental signal decays faster than the theoretical signal, but qualitatively they show the same behavior. So this molecule will decay to the ground state between 100 and 200 femtoseconds because of going through these conical intersections. All right, but that is, so that gives us information about the timescales, okay? But and from the theory, we know that we can watch the molecule and you know that you really have twisting around these double bonds, and actually we quantified how much happens through the different types of conical intersections and so on. But the experimental signal here gave us a lifetime. So how can we get more information about what the molecule is doing from the experimental side? So a different experimental technique that was used from our experimental collaborators was the ultrafast electron diffraction. So while the time-resolved photoelectron spectroscopy is considered as an electronic probe because it probes the electrons, the ultrafast electron diffraction is a structural probe because it creates a diffraction signal because of the position of the atoms in the molecule. And so the way that the experiment was done at SLAC at Stanford. So there is an initial pulse of 200 nanometers that excites the molecule, and then the electron beam interacts after some time delay and gives a diffraction signal. And then from the diffraction signal, we can do a Fourier transform back and get a paired distribution function. So just to understand this more qualitatively with relation to the molecule, this would be the diffractions, the pair distribution function that we get from the signal corresponding to cyclooctadiene, to this molecule. So there are different peaks in the signal, and the peaks correspond to the different carbon-carbon distances, right? So the neighboring carbons have the first peak at the shorter distance, and then you have the 1,3 peak and the 1,4 peak and 1,5 peak and so on, right? So that's how you get the signal. So this signal is for the ground state. And actually here, this is a superposition. It shows both the experimental and the theoretical signal. So the theoretical signal is calculated using the independent atom model. So we don't do electronic structure calculations, actually. We don't consider the electrons at all, but it is the position of the atoms that gives the diffraction signal. But you see that this is actually really good. It's very, very good accuracy between the theory and the experiment. Now, when we look at the signal after the pump probe, after the excitation, then what we look is that what the experimentalists use is the difference of the signal after the time delay minus the signal at time 0. So they plot a different signal. So how do these peaks change after the molecule is being excited and while it evolves on the excited state? So this is a signal that looks like that. Some of the peaks go down, some of the peaks go up. And again, you can see that the theoretical and the experimental signals are in very good agreement. All right, now the overall signal. So we do this. So these signals, we have each one of those for every time frame. So when you put them together, you get a 2D signal like this. And we have these pair distribution functions as a function of the time delay. So this is the experimental signal, and then these are this is the theoretical signal. So the raw signal, and then we smooth it, and well, it looks like good agreement with experiment, but to look at that better, we integrate along the different areas here, and we get these integrated signals. And again, the theory and the experiment agree very well, which is good, but what do we learn from that? So we will focus on this signal here, which shows some oscillation. So there is an oscillation that is found in the experimental signal and is reproduced in the theoretical signal. So what does that correspond to? So because we have the theory, we can go back to our trajectories and see actually where the signal is coming from. And when we analyze the trajectories, we found that the signal that reproduces this oscillation with the same frequency involves a type of breathing of the molecule. So it is these carbons that they are carbon 1,5, but there are two different distances that they change as the molecule breathes. But this breathing tracks the motion of the molecule on the excited state and as it goes to the ground state. So here we see this motion, and the dots correspond to the hops to the ground state. So what we see is that the wave packet starts on the excited state, and it moves along the potential energy surface in a coherent way, and then along this motion, and then it encounters the conical intersections and goes to the ground state. And when it goes to the ground state, then all this 4 or 5 eV of energy becomes vibrational energy, so then you lose all coherence, and the motion becomes completely chaotic. All right, so in a way, then this oscillation that was seen in the experiment is a signature of the non-adiabatic transition and the conical intersections in this molecule. And what is really interesting here is that initially I talked about the conical intersections in terms of the twisting of the double bonds, but now this is a different motion, but this motion is related. It comes from the twisting of the double bonds. Now, the difference is that the twisting of the double bonds is much higher frequency, so it is not possible to see that in the experiment. But this motion that we see here is a lower frequency motion that was able to be detected in the experiment. So in a way, what we have here is an indirect signature of the conical intersections because of this ring system that we can see. And having signatures of conical intersections and non-adiabatic events is always a very important problem in this field. And here the signal again between the theory and the experiment and how well they agree. All right, so so again, this example demonstrated how we can use different probes, and we learned something about the excited state dynamics that is not just the lifetime, but also the structural motion of what the molecule is doing. And using the theory, we can actually validate what the experiment has shown. All right, so now I will talk a little bit about the second example, which involves nitrophenol. So the photochemistry of nitrophenol is important because it can produce these radicals that they are very reactive in atmosphere, and we want to know about this type of photochemistry. So the photochemistry has been studied extensively, and it's actually complicated and different things can happen. So we can have, because the OH and the NO2 groups are next to each other here, you can have excited state proton transfer. You can have again internal conversion to the ground state from these conical intersections. There is also intersystem crossing that is important, and eventually there is fragmentation, right? So these radicals are produced by eventually some type of fragmentation of this molecule. So what is interesting about this molecule is actually that the absorption has two peaks. And this is the theoretical absorption spectrum that we calculated, that you clearly see two peaks here at 5 and 6 eV. And this is the experimental spectrum that also shows the two peaks. Now, there are many, as I said, there are many experiments in this molecule. This molecule has been studied extensively. And okay, so, and these are the different types of experiments. And there are different pump probe experiments. But what is interesting is that not all the experiments use the same excitation wavelength. So there are many experiments that they excite at 330 nanometers, 350 nanometers, which corresponds to the first peak of the spectrum. But there are also experiments that they excite to the higher peak. And again, when these pump probe experiments are being analyzed, it is important to know the underlying. So just looking at the lifetimes is not important. So we want to understand exactly what is happening. So to the start of what is happening is by looking at the excited state. So there are actually 4 excited states in the molecule, and 2 of them are pi star Bryan states. So the 2 peaks in the spectrum correspond to 2 different electronic states. So we did the dynamics for these molecules, starting from each one of the peaks. And this is, so the first thing that we always plot is the population decay, right? So we want to see how fast the population decays to the ground state. So here the dynamic starts from some higher excited state, and then it goes to S1, which is the first excited state, and then it goes to the ground state. So this is like a sequential kinetics model. And this is starting from the high energy peak, and this is starting from the low energy peak. So what is important here is that the time constants that we get by fitting these signals are actually very similar. So in both cases, what we see is that you have a first component which decays really fast, and then you have a second component that rises and decays, rises fast and decays about 300-400 femtoseconds. So by looking at these 2 sets of dynamics, one can say that if we do a pump probe experiment in this molecule, we will actually see the same signal, right? There will not be any difference whether we excite at the low energy peak or the high energy peak. But is the dynamics the same? So again, we have the trajectories. We can see what the dynamics is. So it turns out the dynamics is not the same, even though the timescales are the same. So if we excite at the high energy peak, the first thing that happens when the molecules are on the S1 state is this excited state proton transfer. But how much of this excited state proton transfer happens is very different between the 2 sets of dynamics. So if we start from the high energy peak, we only have 27% of the population doing this proton transfer. But if we start from the low energy peak, we actually have 70% of the population. And this has to do with how close the oxygen atoms come. So the plots here show the oxygen distance as a function of time. And this is this plot here. And the red curve is the percentage of this proton transfer. And we see that they are correlated. So when the molecule starts on the higher energy state, it has more energy, and it looks like it goes to different parts of the potential energy surface, and it does different things. And because the first step is this proton transfer, after that, the things will be different as well, right? So here, these are the conical intersections to the ground state. So the conical intersections are very different in the two cases. In the one case, the conical intersection has this proton transfer structure. In the other case, it doesn't. And then the next step is intersystem crossing. So we also calculated the intersystem crossing. So we didn't include that actually in the dynamics from the beginning, but we calculated the spin-orbit coupling along the trajectories. And then from that, we calculated the probability for intersystem crossing. And we found that actually from both, for both cases, whether you have proton transfer or not, you will have a sufficient amount of intersystem crossing. And then we follow the dynamics on the triplet surfaces, and that's when we see the dissociation. So the dissociation happens only on the triplet surfaces. And the dissociation products are different between the two cases. So when we have proton transfer, there is an OH radical production. But when there is no proton transfer, there is an NO radical production. So the photochemistry here depends on the excitation wavelength. So in summary, we have observed in this molecule that we have very different dynamics depending on where we do the excitation wavelength. But if we only look at timescales, we will not see that. So if we have pan-probe experiments that we only examine the decay scales, the decay times, then we will not see the difference in the dynamics. So one has to be very careful about how we interpret dynamics in molecules. So with that, I will conclude. And I will say that what I try to show in this talk is that so the basic theme is that if we really want to understand what the molecules are doing in the excited states and the non-adiabatic dynamics, we have to do this multimodal approach. We have to think about combining the theory with different kinds of pan-probe experiments to interpret the different parts of what the molecule is doing in terms of electronic structure, but also in terms of the structural deformations. It's also really cool that using the structural ultrafast electron diffraction probe, we can see some signature of these structural deformations as the molecule goes to the ground state. All right, so with that, I will finish my talk here and thank my group for their work, especially Pratip, who did the cyclooctadiene work, and then Daxita, who did the work on the nitrophenol and funding. And thank you for your attention.
Thank you, Spiridoula. All right. So we're in the Q&A session now. So if you have a question, you can either type into the chat using the Q&A feature or raise your hand and I will unmute you. To kick us off here, Sashi Mishra asked, can you describe briefly how you theoretically calculate the time-resolved photoelectron spectroscopy?
Sure. Actually, I have a slide for that. Hold on. Yes. So, this cartoon again shows what the photoelectron spectrum does. So we have the pump that goes to the excited state, and then the probe ionizes the molecule. And when it ionizes the molecule, the signal is the kinetic energy of the ejected electron. Okay, so the signal has two parts again. One part is the kinetic energy of the electron, and we watch that as a function of time. So in order to calculate the signal, we need this energy, the energy of the electron, but we also need information about the intensity of the ionization. The energy, the kinetic energy of the electron, we can get from conservation of energy, basically, right? So we run our trajectories on the excited state, on the molecule, and then we pick snapshots along the trajectory, and for every snapshot, we calculate the ionic states. And then because we know the energy of the ions, we know the energy of the neutrals, we take the difference, we know the energy of the photon that is used in the experiment, and that is, so then the kinetic energy will be the energy of the photon minus the ionization energy. So that part is easy, as long as we have accurate energetics for both the neutral and the cation. Then the second part is the intensity. So the intensity, if we think about the dipole approximation, is the initial state, which is the neutral state in this case, and then the dipole and the final state. The final state is a product of the cation and the electron that is being injected. If we rearrange this integral, then we can take the overlap of the neutral state and the cationic state, and that will give us the Dyson orbital, which is here. And so then the dipole matrix element will be between the Dyson orbital and the continuum electron. So there are many ways to do that. The simplest way that we have done in the work I showed here is that we forgot about the continuum electron. So we only take the intensity, the measure of the intensity comes from the Dyson orbitals. And this works well for many of the cases that we have studied. But if one wants to be more accurate, then they have to treat the continuum electron as well.
Very good. We have another question here from Sarvesh Kumar. In the case of COD, you mentioned twisting along the double bonds causes decoupling of states. Can you please comment on the case where there are no double bonds in a molecule?
If there are no double bonds in a molecule, then the photochemistry will be very different. So I think if you only have sigma bonds, well, you can decay through dissociation. So if you break the sigma bonds, yeah, so it will be very, very different type of photochemistry. And I think the most common would be dissociation along some of the sigma bonds. Also, the excitation will be much higher.
And I had a question on your slide. You showed the competition between excited state proton transfer leading to OH and intersystem crossing to NO. I may have missed it, but the formation of HONO, how is that the intersystem crossing route, or is that the proton transfer, or?
Yeah, the HONO we didn't see in our calculations. Other people have talked about the HONO. In our calculations, we did not see the HONO. But you would need the proton transfer because you want the hydrogen to get HONO. You want the hydrogen to be with the NO2, right? So that should have to happen after the proton transfer, but we did not see it in our calculations.
Very good. Okay. I'm seeing no other questions in the chat. Carl Irakua. Oh, there we go. I will unmute you.
Hi,
go
thanks
ahead,
for
ask
that.
your question.
Thanks for that nice presentation. I'm thinking of the mass spectrometry problem where you have open shell core ionized states or deep valence ionized states. Seems that active space would be impossibly large. So I'm wondering whether that kind of work has been done and what techniques are necessary to handle that kind of thing.
You mean fragmentation of the cation for mass spectra?
Yes.
Yeah. Yeah, that's a hard problem. Because you can break in different parts, right? It is we tried to do something about that long time ago, and we did it with finding pathways, and it was very painful. I cannot think right now the most recent work of what people have tried, but it is indeed a very complicated problem, what you said, because you can break different bonds, and it's not easy. I would think the dynamics may help, but again, you're right. You need a large active space to be able to capture the different things. It's very tricky.
Oh, sorry. Tim Zuer has a question. Tim, go ahead.
Yeah, Spiridoula, very nice talk. And we have some recent results that actually are relevant to the previous question, where we're studying the photochemistry of large ions. One of the things that can be the case is if the charge state itself is not directly a part of the chromophore. And then, of course, you can use all the normal tools that you're used to using, right, for identifying conical intersections in the chromophore part of the molecule. And in fact, we've been studying tyrosine-containing peptides, and so looking at the nitrophenol, I was very interested in that because tyrosine has as its chromophore phenol, and there the photochemistry, involves various things from loss of that tyrosine side chain to peptide backbone breakage. And then also under certain conditions at certain wavelengths and IR excitation, loss of the hydrogen atom from the tyrosine. Do you know, I guess in the nitrophenol case, isn't it, the proton transfer is sort of the equivalent of losing that hydrogen, right? But is it actually a proton that's being transferred, or is it one of these proton coupled electron transfer kind of situations? The net result, right, isn't a cation and an anion, right? So doesn't the electron have to follow the proton?
But you form the carbonyl, right?
Yeah.
On the
Right,
if
I
the
guess in the
proton
end,
leaves, then you form a carbonyl on the other side. So the electron couples to the ring.
okay, yeah, maybe because that electron doesn't have to go like with the proton necessarily, but redistributes around the rest of the molecule or something.
Yeah.
Yeah, okay. I guess I see that. Yes.
Yeah.
And it's blocking the hydrogen atom loss, basically by virtue of that hydrogen bond to the nitro group, right?
Yeah.
Yeah. So you never see that channel that's so important in phenol and its derivative.
Okay. Yeah. In phenol, right? You're right. In phenol, that's very important. Yeah.
Right. Yeah. Thank you.
Yeah.
Oh, wonderful. Well, thank you so much, Spiridoula. Thank you again, Bryan, for giving such wonderful talks here. As we close today's session, as a remind that to please register for our December 12th talks. We have 2 fantastic talks lined up. And also, we are planning our Spring 2026 series. So if you have speakers that you'd like to recommend, please let us know. With that, take care, everybody. Have a wonderful weekend.
Thank you.
Thank you.